All right, so this is our third and last lecture in Chapter 13, Radiation Exchange Between Surfaces. We were introduced to the view factor from, let's say, I to J. There's an equation to calculate it. We never, ever use the analytic equation, which is 1 over AI, the double area integral of the cosine of theta I, cosine of theta j, divided by pi, the distance between the 2 points on the surfaces squared. And then you have the integration over area I, the integration over area j. But nobody uses this equation. We calculate them using tables, and other people have done a lot of hard work to tabulate it in an analytic expression or in a table for the view factor, a bunch of conditions. We were introduced to a geometrical resistance in a radiative network, 1 over AF. And then we had nodes. The nodes were the EB nodes, and what flows between the two nodes, that it's driven by the black body emissive flux, is the resistance is the 1 over AF, and what flows through is the rate of heat transfer, Q. All right. Well, then we added that we could have a gray diffuse surface. First of all, black surfaces are diffuse, but they're not gray, they're black. And then you have the gray, which means the absorptivity is equal to the emissivity, regardless of the wavelength or overall wavelength. So we neglect that. We have another resistance. I call it the geometrical or surface resistance. Surface resistance, 1 minus epsilon over epsilon A. And then it connects an EB node with a J node. What's a J node? Radiosity. Has the same units, and it's what that potential difference drives the flow. What's the flow? Q. And the resistance is the 1 minus epsilon over epsilon A. Okay. Today we'll solve some multimode heat transfer problems. This section is like a paragraph long. Okay, you can skip it if you like. It's about a paragraph long. Smallest section in the textbook, I think, other than some section that just refers to dependencies. And then we're skipping the participating medium. So we have the simple configurations. Let's say you have a 2-surface enclosure. Here's a surface and then a surface here. So this is surface 1. And that's the participating face or side of surface 1. And here is surface 2. Tell me a little bit about surface 1. It's flat. Okay, can any of the photons leave surface 1 and go back and hit surface 1? No. All right, tell me a little bit about surface 2. It's concave. Can any of the photons leave surface 2 and go back and hit surface 2? Yes, they can. So this is going to be greater than 0. We don't know the value of it yet. All right. You can get the area of 1 and the area of 2, and from summation you can view that the view factor from 1 to 2 is 100%. That's where the photons go. And then get the view factor from 2 back to 1, use reciprocity, which, let me just write it, A2 F2 to 1 is equal to A1 F1 to 2, divide by the A2, and now I have the equation for the view factor 2 to 1. If you need it. All right, let's set up a radiative network where the emissivity of this surface is less than 1 and the emissivity of this surface is less than 1. Well, we would have a network. It would be EB1, 1 minus epsilon 1 over epsilon 1 A1 out to J1, radiosity node for surface 1. And then likewise, we'd have J2 and EB2, those two nodes as well, and a surface resistance between them, 1 minus epsilon 2 over epsilon 2 A2. And the last one is a geometrical, how well they see each other. If you didn't have the emissivities, if both surfaces were black, this is the only resistor that would be in the network. It's 1 over AF. It could be 1 over A1 F1 to 2, or 1 over A2 F2 to 1, because reciprocity, they're the same. It's probably easier to write 1 over A1 F1 to 2. Okay. And then what flows into the network is this Q. Okay, clicker question. Answer A or B. Are these three resistors in series or parallel? All right, let's take a look. And we still have a few people that don't know the difference between series and parallel, which is unfortunate. Those three are in series. The easiest resistors to combine to get an equivalent resistance. And so you just add those up. All right. So what we have is you can write one equation for the Q, which is from 1 to 2. Sometimes you just leave Q without a subscript. Sometimes you put a subscript 1 to 2 on it, meaning that it's the flow from 1 to 2. Okay, that's going to be EB1 minus EB2 because I can combine those three resistors in series by summing them. 1 minus epsilon 1 over epsilon 1 A1 plus 1 over A1 F1 to 2 plus 1 minus epsilon 2 over epsilon 2 A2. Something like that. And in this case, where I've drawn it, you can now do some additional simplification. Simplify it a little bit. In this case, what is F1 to 2 equal to? It's 1. Not always, but this case it is. In a lot of cases, you'll have like an inner surface, and it has a view factor to the outer surface of 100%. Okay, if that's true, you can simplify this equation. Q1 to 2 would be something like, you can bring up the A1, and then you would have 1 minus epsilon 1 over epsilon 1 plus 1 plus 1 minus epsilon 2 over epsilon 2 A1 over A2. And then we have sigma T1 to the fourth minus T2 to the fourth. You see that simplification? Sometimes they start simplifying these equations, and I'm not certain it's all that helpful because students think, oh, another thing to memorize. But what you can cancel this 1 with this minus emissivity 1 divided by emissivity 1, and so you have a slightly, Q1 to 2 is equal to A1 sigma T1 to the fourth minus T2 to the fourth divided by 1 over epsilon 1 plus 1 over epsilon 2 minus A1 over A2. Did I do that right? Did I do that right? I'm running out of room, and it looks okay, algebra. This is the better equation to really be able to rederive, but there are sometimes some simplifications which you say, where did that come from? Well, it's just a little algebra. So, two surface enclosures. This is the sketch from the textbook. My discussion of calculating Q1 to 2, 3 resistors, 4 nodes. You can combine, and you can get that Q1 to 2, which is like what's going into node 1, which has to be what's going Q negative. It's out of node 2. See, it's not a positive in. I really don't like this notation, but that's okay. You should just leave that positive Q2 going in and leave it alone. But it's what we just worked out, isn't it? And so really easy to have a 2-surface enclosure exam problem. It's hard to have a 3-surface enclosure exam problem. It's nearly impossible. It's very, very rare to have a 4-surface or more enclosure exam problem. All right. So this is a problem that we worked on last time. You have a plate. It's at 1200 Kelvin. And its emissivity is 1, so it's black. We have another plate at 400 Kelvin. Its emissivity is 0.8. And then we're able to calculate what is that flux, this Q, I'm going to put it per unit area, from 1 to 2 is equal to 92.9 kilowatts per meter squared. A little review. We set that up, solved for the flow. Now, what did we do? I think this is also a review. We stuffed We stuffed a foil. What is that? A radiation shield in between the two. The piece of foil, just like you would get out of the kitchen drawer for the foil. That would be a very good low emissivity on both sides. Okay, so that radiation shield goes in between. When you put that radiation shield in between, it drops it substantially. What was the flux? 92.9 kilowatts per meter squared down to 11. That's a pretty good reduction just by putting a thin sheet of aluminum foil in there. It's a radiant shield. So a lot of times when you want to reduce radiation, you put in radiant shields. That's what you do. They're very effective. And as long as it's sealed and you keep dust from collecting, or if it's not prone to oxidation or sort of surface deposits, it'll stay for a very, very long time with that low emissivity. Okay. Yeah, I think we did this all last time. It sets up a nice long network, and you have J nodes and EB nodes, and it's a little bit of bookkeeping. But what was that? An 88% reduction in Q, going from 90, whatever it was, to 11.3 kilowatts per meter squared. That's a significant reduction. We also covered, so this is a review, reradiating surfaces. So if you have a 3-surface enclosure and one of them is well insulated, that means it's no participation with the outside world. That's a reradiating surface. Okay, so if there's a heat supplied to one, then the heat supplied to surface 2 is really not a heat supply, it's a heat removal at the same magnitude as Q1 going in. Energy balance for the network. Well, you could set up a resistive network. Q1 is coming in, so it's EB1 to J1. The re-radiating surface is insulated, so QR is 0. Hence, it's like this node collapses with that node. The EB of the radiating surface is equal to the J of the radiating surface. The flow that goes this way can only go that way. So now I have these two resistors in series. I can then add them and get an equivalent, then combine it with this resistor. Those two are now in parallel. And then I have 1, 2, 3 in series again. So it's a great example of series, parallel, series reduction to one equivalent resistance. And so then you can put the EB1 minus EB2, and then this is that net equivalent resistance of all those resistors collapsed down. You can tell this is the addition of these parts, and this is that combination of series plus parallel, or then parallel. All right. This equation looks overwhelming, doesn't it? But it's really not overwhelming. I would say if there's a 3-surface enclosure on the exam problem, 50% of the time, one of those surfaces are re-radiating. So we want to make sure to be able to solve a problem like this, right? All right. Let's solve this problem. The end of a cylindrical liquid cryogenic propellant tank in free space is to be protected from external solar radiation by placing a thin metallic shield in front of the tank. So here's my tank that's well insulated on this side. I guess the sun is over here that gives it the solar load. And the shield is placed there. And so they're sketching the solar irradiation. Is that the right symbol? G subscript S? G for irradiation, subscript S for solar? Sure, that's what the book is used throughout. Go back to chapter 1. G subscript S was introduced. Believe it or not. All right, so that's a solar irradiation. And instead of going directly to the surface of the liquid cryogenic propellant tank, it's going to hit on the shield Okay, and the shield has an emissivity on this side, emissivity on that side, and the propellant tank has an emissivity as well. Let's continue to read the problem. Assume the view factor between the tank and the shield is unity, meaning the gap here is so small that it's a one-to-one. There's very few photons that go from the tank surface and go out the gap. The photons just go to the shield, and the shield photons, negligible amount, get out the gap, and most of them go and hit the tank. So it's a one-to-one. It makes it a little easier. That's good. All surfaces are diffuse and gray. We don't have the skills to handle a non-diffuse surface. That's this whole part of this chapter. This is approximation. Okay, it's how the photons are emitted or reflected, and it's cosine distributed off of a surface. It's the regular distribution of photons, like a black surface. So this is good, standard statements. And the surroundings are at 0 Kelvin. What? Where are the surroundings in this problem? Well, the surroundings would be here if some of the photons escape, but that's really not it. The surroundings are over here, so that this side of the shield can radiate to the surroundings. Not this side. This side only radiates with the tank. But the right-hand side of the shield can radiate back into the surroundings. Okay. They are at 0 Kelvin. It's like it's a sink, and it's sending no photons back. The space is so cold, there's negligible photons going back. Only photons hitting that shield are from the sun's solar irradiation. And that's like a light beam. That's like a sun is a speck in the sky, and it's sending the photons, and they just hit like that. Okay. What down here are they going to ask us to calculate? Find the temperature of the shield and the heat flux to the end of the tank. So here's the answers. 338 Kelvin for the temperature of the shield right here, and 25.4 watts per meter squared. Okay, here's some more data we're given. The solar radiation is 1250 watts per meter squared. So that shield's pretty effective in reducing the heat flux that's having to get into that tank, isn't it? Okay, let's do this. What is the emissivity of 1 and the emissivity of 2? 0.05. That means only 1/20th of the photons get absorbed. What happens to the 19 of the 20 photons, the 95% of the photons that impinge on that surface? If they're not absorbed, what happens to them? Reflected, right. Okay, let's take a look. What's the emissivity of the tank surface over here? Well, it's 10%, so 0.10. So this is 0.05, and then 0.10. What happens to 90% of the photons that impinge on the surface of the tank? They're reflected. So its emissivity is 0.1. All right, so how do we calculate this temperature of the shield? And then how do I calculate that heat flux? Should I give you a minute and set up the problem? All right, so what I was looking to do is to have you set up and put a node, and then put that the EB of the tank surface, the corresponding to this tank surface there. And then whenever you have a surface like that, you have the radiosity node for that tank surface. And this resistor right there is 1 minus epsilon over epsilon A. Let me fill that in a minute. And then a shield. This is hard because I have two sides to the shield. Notice that they showed emissivity 1 and emissivity 2. So I'm going to put J2 so it's consistent with this notation 2 on the side 2 of the shield. And then I'm going to put an EB for the shield, and then I'm going to put a J1 for the side of the other side of the shield, consistent. All right. At this point, I'm going to have resistor, resistor, resistor. So I'm not quite done. I have, for the J1, I have this large surroundings that's at 0 Kelvin. Well, you could put in here the J of the, I'll call it sky, and then EB of the sky. All right. And so we would have something like this and something like that. And I'm going to simplify in a minute, but somebody wouldn't really be wrong if they did it this way, but let me just work through a couple steps, and most people wouldn't do that. Okay, this would be a 1 minus epsilon over epsilon A. This would be a 1 over AF. This would be a 1 minus epsilon over epsilon A. This would be a 1 minus epsilon over epsilon A. 1 over AF, and a 1 minus epsilon over epsilon A. I think I got all those resistors correct. Some are geometrical, 1 over AF. Some are surface, 1 minus epsilon over epsilon A. Okay, now, what about this sky over here? How large is the sky? Do they give me how large it is? They really don't. It's huge. The sky is huge. Whenever the sky is huge, what does it do to this 1 minus epsilon over epsilon A in the limit as A goes to infinity? 0. All right. Now another one is, what is 1 minus epsilon over epsilon A in the limit as epsilon goes to 1? 0. So it's kind of funny, and it's a little tricky here. But when you have a very large surface, even if it doesn't quite have to be perfectly black, it effectively acts as if it's black, because the 1 minus epsilon over epsilon A is 0. Make sense? So now that we say, oh, the large sky, we can get rid of or reduce this network, can't we? So we would basically say, that's negligible. And so this becomes the same, and we just have the from J1 out to EB of the sky. Okay. All right, now this is the flow that's getting into the tank, Q into the tank, right? Okay. Now, I have to deal with this solar load. It's 1250 watts per meter squared. If I multiply that by the area of the shield, won't that give me how many watts of solar radiation are impinging on the one surface of the shield? They're impinging on side one of the shield, right? Okay. Can you just tell me how many of the 1250 is absorbed into the shield? Wouldn't it be 5%? It would be 5% of the 1250. Okay, so we've got this term which is area of the shield, the solar irradiation, and the emissivity, which is the same as the absorptivity. So I guess I'm going to put absorptivity of side 1, which is emissivity side 1, because it's gray. It would be 0.05, 5%. Okay, that's like how many watts are being dumped into this network somewhere. Is it dumped into the J node here, dumped in here, dumped in here, dumped in here, dumped in here, or dumped in there? Let's say option A, B, C, D, E, or F. And F is wrong because your clicker won't even allow you to put an F. But hey, keep trying. If you really want F, go ahead and just keep looking for the F key. But you tell me, where do I dump this energy into this network, radiative network, due to the absorption from the solar load? All right, well, this is a challenging modeling question for us. because what are we trying to represent? It's like a Q getting dumped into our network at a node, into a node. Just like this Q is being dumped into our network at that node. Actually, it's coming out because the tank is receiving the energy. All right? So most of us said it's location E, which would be in this node. It's really not that location. So what I'm going to do is I'm going to take away option E, I'm going to take away option F, and I'm going to take away option A. I'm going to take those away. All right? So now all you can vote for is B, C, or D, and then we're going to redo this, close this, and redo. It's the solar load. Where is it getting into some material? All right. Well, this is one of the brightest classes I've ever had. Congratulations. Should I go back and grade the other one? No? I should, just to give this. Oh, it won't let me do it. There it is. All right. So this is just one of those things where you have to think about it long and hard. Maybe I get rid of all this clutter up here and still use a red line indicating this is a load getting into that node in the network. And this is removing a load removal. And right out here, I'm going to simplify this network some. I already talked about that. Let's just put this one, call this what? EB of the sky. And there's going to be some out right there, coming out. And so it's like this. It's like you can say, oh, we have 50 watts coming in. Well, you could have 25 watts going out over here. How many watts would, by conservation of energy, be going out over here to the tank? 25, right? Or let's say they said this is 20 watts over here. What would be coming out to the tank? 30 watts, right? For the, whatever it is. So this is the flow. It takes us a while to figure it all out, but that's our problem. So how about this? Can you tell me? We're going to leave this area in here. Did they tell us this diameter of the tank? Did they tell us a diameter? No. You can pick, and maybe it's easier every now and then to just assume the area is 1 meter squared. And then you know, hey, I'm doing everything per meter squared of the tank. And if you did, maybe then this is a little easier. You would say 1250 times 1 meter squared times 0.05, and I forgot that number. I don't know if I ever ran it. That's how many watts would be coming in. Now I need to do the bookkeeping to see where they go. Okay. All right. Now, so this is coming in. All right. Let's go back here. Do I have enough information to get the EB of the tank? This is equal to sigma temperature of the tank to the 4th power. The temperature of the tank is 100 Kelvin. I can calculate that. This comes in to be 5.67 watts per meter squared. It's just run the number, right? 5.67 watts per meter squared. All right. The EB of the sky, I'm going to pause. I want you to give me the EB of the sky in the correct watts per meter squared unit. I'll get 3 people to give me the correct number either on the calculator or sheet of paper. So this one is 0 watts per meter squared. It's a temperature of 0 Kelvin. It's a sink. It's a really nice, like, ground. You know, it's to the ground, electrical analogy. So what you do is you have to write an energy balance equation. Basically, you could reduce this node right here, which is the EB of the shield, and you would have the flow coming in, which is alpha 1 area of the shield solar irradiation. And then we would have some equivalent resistance out to EB of the sky, which is 0. How do I get this resistance? Sum those two in series, and then have one resistor over here, sum the other 3 resistors in series, And then you would have the EB of the tank, which is 5.67. All right. So we don't know the Q to the tank. We don't know the Q to the sky. How am I going to solve for first of all, the temperature of the shield? This is sigma temperature of the shield to the 4th power, isn't it? Get rid of some of this junk here. Isn't it? Sigma temperature of the shield to the 4th. So if I could get EB of the shield I could then get temperature of the shield. How am I going to do that? Kirchhoff's current law. Energy balance for that node. What does that equation look like? Well, what's an N? Alpha 1, A, surface, G, solar. Okay, and that's then equal to, I'm going to put EB of the shield minus EB of the tank divided by these 3 resistors summed. Well, that's just 1 minus epsilon of the tank divided by epsilon of the tank. I'm going to put 1 for the area. And because we picked the area to be 1, just leave it 1. And then we have plus 1 over AF, 1 times 1, plus 1 minus epsilon of side 2 of the shield, epsilon 2 times 1. Make sense? All right. And then we put in here EB of the shield minus EB of the sky. Hey, professor, we know that's 0. Put 0. Fine. There you go. And then we're going to have the 1 minus epsilon 1 of the side 1, epsilon 1 times the area of 1, plus 1 over 1 times 1. Well, can we just forget about these 1 over AF resistors? No, we need them. We need those 1 over AF resistors. Okay, so you take a look at this equation. This is the only unknown, isn't it? Only unknown? We know this, all of it. I mean, this one I should have put in here for the area of the shield, 1 meter squared. That's our assumption. Okay, well, at that point, you calculate EB, and the EB comes in at, EB of the shield comes in at 742.11. It has funny units. It's watts per meter squared, and it's equal to sigma temperature of the shield to the 4th, and hence you get the temperature of the shield to be 338 Kelvin. Once I have the temperature of the shield, now I can hit what is that heat flux that goes to that end of the tank. Wouldn't it be just this component right here? Isn't that what goes that way? So the Q double prime getting to the tank is equal to the EB of the shield minus the EB of the tank. And then we're going to have 1 minus the epsilon of the tank. And then let me write it out. Let me put it like this, without the flux, and I'll put the area in. Emissivity of the tank area, then you have plus 1 over area view factor, which is 1. And then you have 1 minus epsilon 2 over epsilon 2 area. If you multiply both sides of the equations by 1 over A, it cancels all these A's because they're all the same area. And now I have it in terms of flux. Okay. And let me just leave it as an exercise. Then the flux is the EB of the surface, 742.11, of the tank, 5.67, divided by 1 minus 0.1 over 0.1 plus 1 plus 1 minus 0.05 divided by 0.05. and then you calculate 25.4 watts per meter squared. For those that struggled with this problem earlier in the homework, did the explanation help? One, did it help? Where do I suspect most students would have problems? They wouldn't know where to put this energy into the network. Don't put it into a radiosity node. Put it into a surface which is represented by sigma t to the fourth. Okay? Just put it into the EB node for that shield. And you have to only put in what is absorbed. What's reflected just is reflected back out to the sky. Okay? All right, you ready for another problem? Consider a cylindrical cavity of diameter 100 millimeter and a depth of 50 millimeter, whose sidewall and bottom are diffuse and gray with the emissivity of 0.6 and are at a uniform temperature of 1500 Kelvin. Again, every engineering problem you have to read each sentence about 3 or 4 times to understand. Unpack it. There's a lot of information in there. The top of the cavity, so we have a cylindrical cavity. Think of a surface like this, and then there's a hole, and there you go, and then it goes like that. And that's our cylindrical cavity. Okay? All right. The top of the cavity is open and exposed to surroundings that are large and at 300 Kelvin. When you have a large surroundings, what is the effective emissivity of the surroundings? 1. We just went through that discussion. It's 1 because it has the same effect of reducing any surface resistance with the large surroundings. All right. Calculate the net radiation heat transfer from the cavity, treating the bottom and side wall of the cavity as one surface. And then call that Q sub A, and here's the answer, 1841.6 watts. So, if you did it that way, it would be a two-surface enclosure where the surface 1 is going to be, let me try and draw it like this. This is L, the depth. L was 50 millimeters, and this is D, the diameter, which is 100 millimeters. And so the area is going to be the sum of the pi dl plus the pi d squared over 4. That'll be the area of the inside. And all of that temperature of the inside was given to be 1500 Kelvin. Okay, what about the area 2? Well, we have an infinite enclosure here, but what you do is you just put 2 as the lid to close it. And you treat it black with the emissivity 1. And so the area 2 is pi d squared over 4, and its temperature of 2 is 300 Kelvin, and it's treated, emissivity 2, as black. So every photon that comes up and strikes on it, that imaginary lid is absorbed. Okay. And so the emissivity of the other surfaces down here is all at 0.6. Well, this one we can solve, can't we? The only thing we have to do is we have to get the view factor. Let me write out the network. We'll have EB1, we'll have J1. We don't need a J2 because it's a black surface, but we have an EB2 surface node. Okay, so we have a 1 minus epsilon 1 over epsilon 1 A1. Then we're going to have this 1 over AF. Okay. Since it's hot, I'm going to put in the Q1 this way, and we'll draw it like that, but this Q2 is going to be negative Q1. All right. So, I left a little room right here. Do you think it would be easier to put here that this is either 1 over A1 F1 to 2, or should I put 1 over A2 F2 back to 1, answer A or B. Which one do you think is a little easier? All right, so why is A2 F2 to 1 a little easier? Yeah, because the view factor from 2 back to 1 is unity. That's why. So it's like there's 4 things to think about. A1, hey, no problem. A2, no problem. Haha, these view factors, they're always a challenge. But after you've done a few of them, oh, this one is unity. This one, 1 to 2, is not unity. And actually, the way I would calculate 1 to 2 is using reciprocity, which is essentially A1 to 2 is, A2 to 1 divided by, or times A2 over A1. So I basically, to calculate view factor 1 to 2, I would use the fact that I can calculate 2 to 1 first. So why not just use 2 to 1? So A2 F2 to 1. A little easier? All right. Okay. Do I have enough information to get this sigma T1 to the 4th? Sure. Do I have this one, sigma T to the 4th? Sure. I have both of those. And so you can now calculate the flow, and this Q will be sigma T1 to the 4th minus T2 or sky to the 4th divided by the 1 minus the epsilon 1, which is 0.6, divided by 0.6. You do have to do a little work to get A1, don't you? We already described that. Here's the equation for A1. And then you have the 1 over A2, which is it's pretty easy, times the view factor 2 back to 1. And there you go. So you would then calculate that this is 1841.6 watts. 5 significant digits. Why did we leave 5? Because the part B says to recalculate, but don't assume that these all have the same, treat them as the bottom of it as a different surface than the sidewalls. And what they're getting at is the radiosity from the sidewall is a combination of what's reflected off the sidewall as well as what's emitted off the sidewall. And quite frankly, near the top part of the sidewall, it's seeing a lot more photons impinge on it from the sky or the lid. And hence its reflection is a little different than the reflection from the bottom of the sidewall or from the middle of the bottom. It's a little subtlety, but it's an important subtlety. But for this problem, you're going to get a slightly different answer, and that's why. When you treat the sidewall separate from the bottom. Okay, so let's draw our network. So we're going to have let's do this, put the EB of the sidewall, EB of the bottom, EB of the top, and now I have a J of the side, a J of the bottom, and then we just have this resistors like this. So we have 1 minus epsilon over epsilon A, 1 minus epsilon over epsilon A, 1 over AF, 1 over AF, 1 over AF. I should have expanded it, left more room, sorry. But does that make sense? And now you say to yourself, okay, I know the EB of the side, I know the EB of the bottom, I know the EB of the top. I do not know the J of the side and the J of the bottom. That's a rub, that's a problem. But what I want to calculate is the net radiation heat transfer from the cavity, which is going to be the sum here, Q of the side, Q of the bottom, and so it's like the sum Q of the side plus Q of the bottom. That's what I'm trying to calculate. How do I do that? Well, if you could get JS, solve for JS somehow, then from the side it's EBS minus JS divided by 1 minus epsilon over epsilon A for the side. And then for the bottom, it would be the EB black on the bottom minus J of the bottom divided by 1 minus epsilon over epsilon A for the bottom. So it hinges on getting JS and JB. What are the radiosity for the side and the bottom surfaces? Okay, I have two unknowns. Two unknowns. What are they again? The radiosity in the side, the radiosity in the bottom. Mathematically, go way back, way back, pre-calculus days, right? How many equations do I need if I want to solve for two unknowns? Two. Where are you going to get two equations in order to solve for JS and JB? The network helps you. How are you going to do it? KBL or KCL? Do those little acronyms mean anything? Kirchhoff's law for voltage, that's over a loop in our network. Kirchhoff's current law for a node. The flow of the current into any node in a network must equal to 0. That's the second one. Which one are we going to use? This one, it's an energy balance equivalent for the nodes. What node? Well, probably pick the nodes that you want equations for. Pick this node right here, which is the JS node, and then pick this node. Do an energy flow into those two nodes. And those will give you two equations. Let me scoot down so I can work on this a little bit. So for, let's say, the energy balance for the JS node, what does that equation look like? It'll be EBS minus JS divided by 1 minus epsilon over epsilon A for the sidewall. Then I'll have EB tank minus JS 1 over AF. And this area is going to be, I'm going to say that the area of the tank to sidewall, or it could be area sidewall, view factor sidewall to top, top of the tank or lid or something. This is T for top. Okay, I think I said tank, but it's mistaken. Tank, top. And then we have plus J of B minus J sub S divided by 1 over AF. Well, this is going to be either from the area of the bottom, the view factor from bottom to sidewall, or you could again, reciprocity, I could replace that area view factor by area sidewall view factor sidewall to top, just like I could replace it by area sidewall view factor sidewall to bottom. All right, these three have to sum to 0. I didn't leave enough room right there, so I'll write it like that. Those sum to 0. The flows into a node have to be equal to 0. Into what node? The JS node in the network. That equation has two unknowns. We get another equation, which is the energy balance for the JB node. This is the energy balance for the JS node. Okay, so 0 is equal to, it looks very similar. It's going to be EB of the bottom minus J of the bottom divided by 1 minus epsilon over epsilon A of the bottom. Then we're going to have B of the top minus J of the bottom divided by 1 over the area, let's pick bottom, view factor bottom to top, plus not EB, it's a J of the side minus J of the bottom divided by 1 over area side view factor side to bottom. Professor, I really don't know how to solve two equations and two unknowns. Yes, you do. It's linear algebraic. They're the easiest ones. They're not even nonlinear. There's plenty of ways to do that. Professor, I have a calculator I can use on my exam. Can I use it to solve a problem? Yes, you can, right? Beat it up. Solve it. So when you solve this network problem, you get the solution for the J's. My solution came in that J of the bottom was 230,896. What units does it have? Watts per meter squared. The J of the side is 237,040 watts per meter squared. It's a little higher. All right. Did I do that calculation correct? For some odd reason, the numbers don't look perfect to me. But once I have those, then I can come back to this equation, which I just wanted to get. What is the Q from the side? And then what is the Q from the bottom? I calculate them, because I calculated JS and JB. Add them up, and I get almost the same exact number. But it's slightly lower. Okay. Any questions about that? Did it look okay? You ready? Continue on? All right. Well, this one is another challenging problem. We have a long uniform rod of a given diameter, and the thermal conductivity is given, and it's heated internally by a volumetric heat generation rate. Hey, that was our old Q dot. That's our volumetric heat generation rate. Wasn't that out of like chapter 3 or something? Deja vu, right? Long time no see, but hey, here it is again. So it's 20,000 watts per meter cubed. The rod is positioned coaxially, we understand that, lined up in the middle of a large circular tube of 60 millimeter diameter. So the thing is very large. Now, I read this problem once or twice and I said, is it oriented horizontally or vertically? Didn't say. Let's pick horizontal. So here's our inner, here's our outer. The inner is solid, the outer is just a shell, but it's very, very long. Okay. The annular region between the rod and the tube is evacuated. Can you have conduction or convection in an evacuated annulus? No, only radiation. Only radiation in that evacuated inner annulus. Surfaces are diffuse and gray with the emissivity of 0.2. Determine the center temperature and surface temperatures of the rod. So where's the rod again? Right there. So the rod has a center temperature, Ts, and a, maybe I should put Tc for center, and then the surface temperature S. The temperature at the center is a temperature at R equal to 0. The temperature at the surface is the temperature at R equal to R naught. For this problem, it's a diameter of 50 millimeters, so the R naught is 25 millimeter. That outer radius. Okay. Well, two temperatures to solve. The surface temperature is solved by radiation. Then how do I get that center temperature? Go back to that previous chapter where you had this heat generation inside the rod and you had this distribution of temperature like that where you knew the Ts here and you're looking for T max. And what was my equation? Take a look here at my notes. You find that the temperature as a function of location R is equal to Q dot times R naught squared divided by 4K times 1 minus R over R naught quantity squared plus Ts. So I have to get the surface temperature. I know the volumetric source. I know the radius. I know the thermal conductivity. If I want it at the maximum, at the middle, that means this R goes to 0 That drops this off, and I'm able to solve. Take a look at the two temperatures. Surface versus center. 0.2 Kelvin different. Not much of a difference. Okay? So this contributes 0.2 Kelvin in the results. Okay, but how do I get now the surface temperature of 792.2 Kelvin? I have to do that with radiation exchange. This is a two-surface enclosure, so it's a little easier on the equations. Let me do this in the interest of time because I see I have like 7 minutes left. Let's talk about part B. Determine the center and surface temperatures of the rod if atmospheric air occupies the annular space. Well, you can look head on to it. Here's the rod. Here is my, and I have air all in here. How can the air, what can the air do to change the temperature of the surface and change the temperature of the center line of that rod? It'd be conduction or convection out. For this problem, you can chase the bunny rabbit of convection, and you'll find that it's essentially stagnant air. So if it's stagnant air, no Rayleigh number, significant contribution, or Nusselt number, buoyancy-driven convection in the annulus. Look at the diameters. It's 50 millimeter diameter of the rod and only 60 millimeter diameter of that larger tube. There's not much of a gap. It's like 5 millimeter, 5 millimeter. So it's not a very large gap. So conduction, okay, through there, stagnant air. So what we would do is we have to have an energy balance for the radiation combined with an energy balance for the conduction, heat transfer. And so that'll make you think a little bit, won't it? So what do we do is I would write like this. I would say the Q for the radiation plus the Q for the conduction is what total goes through the system. And what total goes through the system is Q dot times, let's say, pi d squared over 4 times L. L would be this length here, going back that way. And they said L was long. You could pick L as 1 meter, or you could divide through the equations by L, either way. So this is like the source, and it all has to get out. It has to get out by radiation or conduction, but the combination. So how's the model for the conduction transfer? It would be the temperature, surface minus the temperature. Did they give a number for this one? They do. It's the 500. Temperature outer is 500 degrees C. Add 273, 773 Kelvin. So I'm going to call that temperature outer. All right. You divide that by a conduction resistance through a layer in the cylindrical coordinate system. It's a 2 pi KL divided by the natural log of R naught over R. And I'm messing up the symbols here. Let's put R naught over RS there. Does that make sense? So you can put the natural log of the diameters. I think I messed that up. Oh, I messed it up. I got to put it like this. Sorry. It's either the natural log of the radius of the, I'm messing up my symbols, the radius of the outer divided by the radius of the surface of the rod, divided by the 2 pi KL, flip that up, multiply there, and now you have the conduction. And the radiation you repeat that you had before. All right. Equal to Q dot pi d. This is d rad squared divided by 4L. You can see that these L's are going to cancel. Similarly for the radiation. Okay, let me finish out the radiation part of the equation. You put the sigma temperature of that surface to the fourth minus the temperature of the outer to the fourth. That temperature outer was 773 Kelvin. Okay. And then what do we have here? We have a 1 minus epsilon over epsilon area pi dl. The view factor 1 over AF. Go from the inner surface, which is S to naught, and that view factor S to naught is 1. From the inner pipe to the outer surface is view factor 1. Okay, that way this one is pi dl. You can see those L's are all going to cancel. Plus 1 minus epsilon over epsilon pi d outer L. Okay, that d outer was 60 millimeters. This d and that d are 50 millimeters. So you have to keep track of your diameters. Okay, you got the inner diameter, you got the outer diameter. All right, so basically those L's cancel. All right, so this emissivity was 0.2, 0.2, 0.2. View factors 1. I have an equation. All right, this equation is a little different than the previous one because it has Ts and Ts to the fourth. So yeah, on your calculator, you need to be able to solve for the roots of this equation. If you're doing the homework, you've run into that, right? Sometimes you can calculate the EB. Great, I got a number, and then that's equal to sigma T to the fourth, and then I can get the temperature. But in this case, I can't as easily do that. I really need to solve for the roots of a nonlinear algebraic equation. All right, for this problem, you get 783. Lower temperature because there's some heat removed by the conduction path. And then the lower, it's still a delta T boost from the edge to the center line of that rod of 0.2 degrees. So it's a change of 0.2 Kelvin. Well, with that, I just remind you, this is a tough chapter. Really, this is not much to this one. You could just basically skip it as well. Multi-mode heat transfer, I tried to solve some problems today. Pretty challenging. Hopefully you are solving the homework problems. And I'll see you for the exam, final exam. Thank you very much for your attention.